Okay, this time we are going to find the eigenfunctions and eigenvalues for a different boundary condition, y prime of 0 equal to 0 and y prime of 2 equals to 0. And there's several other conditions you can put. So for example, you could have no prime for y0, but the prime for the other one. You can also have like y plus y prime evaluated at 0 equal to 0. There are many different things you can do with this, and they will all have different eigenvalues and eigenfunctions. But we're going to take it for a given that when you rewrite this, as a negative, okay, if you move this to the other side and rewrite it as a negative second derivative, right, like that, this one will always have as non-negative eigenvalues. So we're just going to accept this as a fact. And I mean, if you change the operator, of course, this is no longer true. But there's a mathematical reason why for this operator in specific, it's non-negative. That has to do with the fact that Laplacian is non-negative. That's a much more complicated discussion, so we'll just accept that. The reason I like this is because when you write down the solution, I explained that you have to do three cases: when lambda is positive, lambda is negative, and lambda is 0. But if we know this, we can skip the lambda negative part. Okay? You could try it, and you'll still get the same result. You'll see that lambda negative doesn't yield any eigenvalues at all. You can do it by hand, but we'll just take that as a general theorem for any kind of boundary conditions. Right? Okay, so we'll just do two cases. Case 1, where lambda is 0. If lambda is 0, then if y double prime plus 0 y equal to 0, which means there's nothing there, so it's just y double prime equal to 0. In the last example, I wrote down the characteristic polynomial for this, which is r squared plus 0 equal to 0. But there's a simple array. We can just solve this directly by integrating both sides, right? If you integrate y double prime, you get y prime. And what do you get if you integrate 0?
Constant.
You get a constant, right? And we'll just call that constant b. No, a. Sorry, a. Okay, and then we can integrate one more time to get y, right? So y is, if you integrate a constant, you get ax, right? And then you have another constant, which is b. Okay. So with this, let's now apply the two boundary conditions, which is y prime of 0. Well, the derivative of this is just a. So if we differentiate this and then plug in 0, the derivative is just a, so even if you plug in 0, it's just still a. And because y prime of 0 is 0, 0 equals to a. That's what we get. And then y prime of 2 means you differentiate this and then plug in x equals to 2. Again, derivative is a, which is a constant function. Whether you plug in 2 or 0, it doesn't matter. It still gives you a, so you get 0. Therefore, a equals to 0 will allow both conditions to be satisfied, and you end up with y just equals to b. And because b can be any number, we can definitely choose a number that's not 0, so we do get a non-zero or non-trivial solution. If you have a non-trivial solution, then you call that an eigenfunction, and the corresponding value lambda equal to 0 will be an eigenvalue. Yeah. It's a simple question. I don't know why you couldn't answer that. Right. So we do see that lambda equal to 0 is an eigenvalue with the eigenfunction some non-zero number. We can choose it to be 1. Okay. That would be a convenient value. Now we do case 2, where lambda is positive. And if we didn't have this theorem, we will have to do a case 3, which is lambda negative, but we'll just skip that part by using this. Okay. Now in that case, you just have y double prime plus lambda y equals to 0, with the characteristic equation being r squared plus lambda equals to 0. Solve for r squared. Is r squared equal to negative lambda, r equals to plus minus square root of negative lambda, which is plus minus square root of lambda I. And then we have, okay, that means y is equal to, well, the general formula is if you have alpha plus minus beta I, then it's e to the alpha x, then c1 cosine beta x plus c2 sine beta x. But in our case, alpha is 0, right? So this is just 0, and e to 0th power is just 1. And beta here is square root of lambda, so we get y equals to just c1 cosine square root of lambda x plus c2 sine square root of lambda x. Now you use the fact that y prime of 0 is 0, and the derivative of this would be negative, if you differentiate this, square root of lambda comes outside because of the chain rule, so c1 square root of lambda cosine of square root of lambda, no, sine square root of lambda x, but you're plugging in 0 into x, plus c2, again square root of lambda comes outside because of the chain rule, sine differentiates to cosine square root of lambda times 0. Sine 0 is 0, cosine 0 is 1, so you end up with c2 times square root of lambda. Now, we do know that lambda is positive, so this is a non-zero value, so the only way that this could equal to 0 would be if c2 is 0. So we have c2 as 0. Now let's apply the other condition, which is y prime of 2 is 0. And it's still the same derivative, except that now we're plugging in 2. Right? c2 is 0, so we're not even going to write this. So we have negative c1 square root of lambda times sine of square root of lambda times 2 equals to 0. So either c1 is 0 or sine of square root of lambda times 2 is 0. We already know that lambda is not 0, so that can't be 0. So either c1 is 0 or sine of square root of lambda times 2 is 0. Okay, can c1 be 0? What goes wrong if c1 is 0?
Not an eigenfunction.
It's not an eigenfunction because you get a trivial solution. If both c1 and, since we already have c2 as 0, if c1 is also 0, then they're both 0, and that's not an eigenfunction, right? Yeah. It's a trivial solution. We don't want that. So c1 equals to 0 makes y a trivial solution. Therefore, we must have this. And when is this true? Sine is 0 when? The thing inside is n pi. So, that means lambda would be n pi over 2 squared. Okay? And in that case, the cosine square root of lambda x would be y equals to c1 times cosine n pi over 2x. Right? Because the square root of lambda would be just n pi over 2. Okay. All right, so we're done. So now let's write down the answer to this question. So what's the answer? Eigenvalues are lambda equals to n squared pi squared over 4 with eigenfunctions y equals to cosine n pi over 2x. And just like how I explained, we don't want to write C1. C1 is just some multiple. We just write down one representative of the eigenfunction. Just like any multiple of an eigenvector is again an eigenvector, but you just write one of them, right? Same thing here. You just write one of them. It's okay if you put a 2 or 3 or something else. You just write one of them, okay? And 1 is the most natural one, so you just write 1, okay? And then here's a very important thing. What are the possible values for n here? Huh?
1, 2, 3, 4.
N could be 1, 2, 3, 4 because here it should be, lambda should be positive, right? Yeah. And for this to work, n has to be 1, 2, 3, 4. However, what about this one? Well, this is a case where n is 0, right? If you plug in 0, n equals to 0 would lead to this case. So what you see is after looking at these two possible solutions, we know that lambda equal to 0 is an eigenvalue. So if I plug in n equals to 0, you get cosine of 0, which is 1, which is the eigenfunction for lambda equal to 0, with the eigenvalue 0. So n equals to 0 contains this case. Therefore, and this is the very important point, when you write this on the exam, forgetting this will cost you 1 point, okay? Whatever that question is, right? And the important thing is, for n equals to 0, 1, 2, 3, and so on and so on, okay? So whether it's 0 or 1 or something else, it's very important that you write down the possible values for n. Okay?